Okay, sir. Yes, it's good afternoon, and I would like to welcome. Good evening, in fact, it's past 4 o'clock, and I would like to welcome each and every one of you, especially Amruta over here. And I know Amruta right since she was just 2.5 years old. First time I saw her was when she was 2.5 years old, and then I remember very well her sitting in our CY class in room number 37, bench number 3, third bench towards the window. Am I right, Amruta?
Oh my God, I don't
And
remember.
and she will be looking at her and listening to teachers so sincerely, so enthusiastically, and looking at her eyes, you can make out whether she has actually accepted your point or she has some queries, some doubts about the point that you are making. So from her eyes, you can immediately make out whether you are really preaching through or not. But in the class, she will never open up. She will never disturb the teacher. She will have whatever her doubt she has. She will come after the class and then she will discuss with you. And right till almost till end of TY, she never showed up that as if she's such a good student that others would envy her and all. No, she was always taking backseat. After doing her graduation, she was the only student who got selected from Pune University MSc because uh, Pune University used to take only one student per university other than Pune University for every other university, and from Bombay University she got that seat. She passed out in 2009. That time we didn't have autonomy, so her batch was appearing for university exams, Mumbai University exams, and she stood first in physics in her batch in the University of Mumbai. And after that, her journey, I have requested her to discuss that with you because I want her to tell you what struggles she has gone through, what points you should remember, what you should avoid, what you should take from her to go further. So she's supposed to give you the idea about her struggle. She has done her PhD from Nottingham University, but she has done some projects at TIFR, then at Institute of Science, Bangalore. Am I right, Amrita? You were
RRI,
there at
Raman
Institute
Research.
of Science, Raman Research Institute, Bangalore for a few years. So she will give you some idea about her whole journey from after leaving Xavier's, that is from the step she came out of Xavier's till today. So this is what I would again like to welcome her and give you some idea about this whole journey. Thank you, Amrita.
Thank
Thank
you,
you,
ma'am,
Emma.
for such a nice introduction. I can share my screen now. Yes, thank you, everyone. First, thank you, Bodhne ma'am, for inviting me. It's an honor to share my experience with current students, and hopefully, it'll be a little bit useful because, as she said, I have had my share of struggles and successes, everything. So I hope you find my experience useful to you. So actually, just, just hide this. Um, as Bodhimam said, I'm doing my postdoctoral researcher. Currently, I'm in Israel. I'm here for the past 2 months. I think I'll be here for a couple of years more. But until 2 months ago, I was in the UK, and I think I was in the UK for almost 7 years. I did my PhD there. I also did one postdoctoral uh, research contract there, and just recently I have moved here. So during this pandemic, the work we did in University of Sussex uh, became famous. It was caught in media, and you might have seen this picture of me with a Bose-Einstein condensate on my screen. And I thought I will talk to you about my journey right from Xavier's to the stage of achieving Bose-Einstein condensate from home, and tell you a little bit about what is a Bose-Einstein condensate and why is it a big deal. So stop me at any point if you have any questions. So let me introduce myself, even though Bodhimam has already told most of it. Uh, I was in 2009 TY batch in Xavier's, and yesterday I was thinking of what I should talk to you about, and I was going through some of the old pictures, and I thought I should share some of the memories with the current students because um, 3 years in Xavier's was one of the best experiences of my life. That kind of set the uh, s- floor for rest of my academic career. So it was very nice experience that I would like to show you some pictures. This is me graduating in 2009, and this was the uh, teachers back then, and you know most of them. I think some of them have retired.
They will
And
know only the three ladies in front and Rajesh sir behind. They won't know other three teachers. That is Professor Patwardhan, Professor Diwan, and Professor Amita. That
Anshuk,
these three teachers.
yes. Okay,
Go
so
ahead.
you know 4 out of 7. So that's good. And I also realized that I think we were the first batch who started this quiz called Spectaculum. I think Rajesh sir was very actively involved in organizing this quiz, and it was an amazing experience. It taught us some organizational skills that came very handy later on. So, other than the very nice curriculum, there was also honors program, which I would specifically like to mention here because I think that is something that helped me a lot. And these are some of the courses that I remember were very useful. Jyoti ma'am took astrophysics, Veda ma'am took optics, Bodhna ma'am did vacuum technology, and Rajesh sir did some display technologies. And I want to mention this because I strongly would like to advise current students that do as many projects other than your curriculum as possible because you never know which kind of tool will be handy to you later in your research. I never thought vacuum technology would be such an important thing, but to this day, even my day-to-day research requires knowledge of vacuum technology and optics to great detail. So you never know, and especially research these days is becoming very interdisciplinary. So with that and keeping that in mind, you need expertise from or knowledge from different fields, even though you're not directly working in that field. So it's, I think, very important to expose yourself to variety of topics, and that will also give you some idea about what topic interests you more or what are you passionate about. So this is my strong advice to do many projects as possible and expand your knowledge right at this point. So this was back in Xavier's until 2009, but as you approach TY, you start to think about what you want to do next. Where do you want to do your masters? So I was in the similar state, and I started taking all sorts of entrance tests. So there was, of course, IIT entrance test, Pune University test. I think JAM is after masters. JE is after BSc. So I took all sorts of entrance tests possible. Back then, I think ISER didn't have ISERs weren't in the picture, or maybe they were just coming up. So I didn't take any ISER tests, but you can now do entrance tests for all research institutes. Either you can go for integrated PhD, like combine masters and PhD, or you can just do masters. So I was advised back then to first of all not go abroad for masters, do masters from India, and I agree that I think the quality of masters is much nicer in India. And so, as Bodhna ma'am said, that I got into Pune University and I decided to uh, join Pune University for masters. So I chose specialization of condensed matter physics, even though I'm not doing any condensed matter physics now. But what changed my research interest is when I did this internship in TIFR. It's called Visiting Students Research Program. I'm not sure if it still exists, but this was a internship program in summer vacation of between your year 1 and year 2 of masters, and I had applied for this. And it was a happy coincidence because back then I wanted to do, like every student in physics, I wanted to do high energy physics, go to CERN, and I didn't know what other fields exist. And so I applied at TFR for in the group of high energy physics, but for historical reasons, Professor Unnikrishnan's lab was part of high energy physics, and they deal with lowest possible energy scales, and that lab was part of high energy physics group. And I was assigned randomly this particular lab within high energy physics group, and this is coincidentally the lab which made first Bose-Einstein condensate of India, and I was extremely lucky to have done a project there. So I spent 2 months in his lab doing a project, not exactly Bose-Einstein condensate, but a smaller setup on the site. And that's when I got to learn and got a feel of this field. So I liked it so much that I decided to continue in the same lab for my master's project. And uh, I was given enough freedom from Pune University that even though I was doing my coursework in Pune, I could travel maybe 2 or 3 days a week to Mumbai and do my master's project in TIFR. It was very hectic, but ultimately it helped me a lot getting my next positions because that what I gained was direct research experience in world class laboratory. So this was extremely helpful, and as you will hear about these magneto-optical traps later in my talk, I worked on this project which was directly relevant to the research I got into later on. So this is until masters, and then like every student, I was in dilemma where I want to do my PhD, whether I want to do it in India. I wasn't considering Europe so much at the time. Mainly it was US. So I was giving GRE and TOEFL and everything, looking at universities. But somehow things didn't work out with US applications. But I had also given other exams like IIC and GATE and JEST, etc., so that I have a backup option. And luckily, I cleared GATE with good marks, I think, and it gave me PhD positions in a couple of institutes in India. So I visited these institutes. I think I went to PRL in Ahmedabad, some IITs, and Raman Research Institute, just to get a feel of how the environment is. I gave interviews there. Um, and ultimately, I decided that I like RRI the most. The vibe in RRI was very good. And I was also selected mainly because I had experience in cold atom laboratory already by master's, by the time I finished my master's. So this was a very big plus point. So an RRI has few labs which work in cold atoms. So I decided to join RRI and started my sort of PhD there. But then I got a better opportunity after doing 1 year of coursework. So I moved to UK, but I'll talk about it in a minute. But before, so when you are making this choice, I would strongly encourage you to think about all the aspects. When I was considering, I don't think I only looked at what area I like at the time. And I think that that's not a very good strategy. Given my experience, I would encourage you to think about all the aspects, including financial aspects or family life or what you want to do after PhD. This is something I didn't think much about back then. I just wanted to do, I liked cold atoms, I wanted to do research, I wanted to get PhD, and I was extremely motivated to do that. But I didn't think too much about what after PhD. And this is something I urge you to do a little bit of thinking before you start your PhD. Uh, this is going to be very useful. So about doing PhD in Europe, as you see on the slide, most of the universities in Europe don't have much of coursework. So PhD is relatively quicker. So if you want to just get a degree and maybe move out of academia and get into industry, doing European PhD is a good option. But that really depends on what you want to do. Whether you want to continue in academia, set up your own lab, then European PhD may not be the best option, because you want to gain more experience and become independent researcher, which you will get in a longer PhD. So think about all the options, and the other options that I didn't think, or I didn't have information about back then, is Israel, Singapore, Japan, New Zealand, Australia. But some of my friends have done PhDs in those countries, and now that I'm in Israel, I strongly recommend Israel. The work culture here is very nice. There's amazing drive to do very good science here. So I highly recommend looking into these options. And I think they accept GRE as entrance exam as well. So this is something you can look into as well. So to summarize, I started after BSc, I went to Pune, and then I started my PhD in Raman Research Institute. But after 1 year of coursework in RRI, I met some professors from UK while I was doing one conference, and there was this opportunity of getting Marie Curie Fellowship, which is a very prestigious fellowship. And I got this opportunity to do PhD through this fellowship in Nottingham, and I took it, and it was an amazing experience because Marie Curie fellowships are a bit special. You can travel a lot, you can collaborate a lot, and during my PhD itself, I got exposure to industry and um, a lot of different fields, like subfields within our research area. So it was an amazing experience. So unfortunately, when I was finishing my PhD in Nottingham, my PhD was about building a setup to get Bose-Einstein condensate and do experiments with it. But unfortunately, by the end of my PhD, my group moved to University of Sussex. My supervisor got better opportunities in Sussex, and the whole lab moved to Sussex. So I didn't get many results from Nottingham, but after submitting my thesis, I moved to University of Sussex as well, and there we rebuilt basically what we had started in Nottingham. But we had already learned a lot in Nottingham, and we did modifications on the problems, and we built a better system in University of Sussex. So last 2 years, I was a postdoctoral researcher in Sussex, building an apparatus to get Bose-Einstein condensate and then do further experiment. So finally, in during coronavirus lockdown, so we were very close to reaching the condensate before lockdown happened. Just a day before UK announced its lockdown, we had gotten we had achieved a very important step in the process, and we were all very excited. But then came lockdown, and we couldn't go in the labs. So we were wondering how we can keep progressing about lab work. So luckily we had some of the infrastructure already set up, and because we knew lockdown is coming, we also made preparations, and we were able to sort of keep the experiments going. I was able to run um, I will show you pictures later. It's a very, very complex setup, and run that from home is it seemed almost unimaginable before, but because of the situation, we were able to do that, and we were fortunate that we got this condensate during the lockdown. So it was a big deal, and we are just starting to do some experiments with that condensate in Sussex. But then my contract was ending, and I got this opportunity in Weizmann Institute of Science in Israel. So I decided to make a move, but I still keep collaborating with Sussex Group, and we still have collaboration going on. So this has been my journey. And the next part, I would like to talk about the Bose-Einstein condensate itself. But if you have any questions so far, I'm happy to answer. Okay. So I'll talk about what is Bose-Einstein condensate and why is it a big deal. So first, let's talk very briefly about what it is. And trust me, this is the only equation you will see in this slide. There are no more equations. So as everyone knows, there are like three states of the most common states are solid, liquid, and gas. And depending on the temperature and density of the matter, you can have either matter in solid state or liquid state or gaseous state. So in early 1920s or 1930s, people were doing a lot of studies about what happens to atoms if you go to extremely low densities and extremely low temperatures. So this was when the quantum mechanics was so when you go to this kind of low temperatures, the quantum mechanical effect starts dominating. And you may have heard about wave particle duality, which basically states that every matter can exhibit wave nature, and the associated wavelength of this matter wave can be given by de Broglie wavelength. De Broglie was the one who put forward this idea for the first time. And if you look at this equation here, the de Broglie wavelength depends on the temperature of the atoms. So if you start getting colder and colder, at some point this wavelength becomes very large. So maybe in the next slide you can see it better that when you're at high temperature, you can treat your particles or atoms as classical spheres. This is where everything is described by classical physics or Newtonian physics. But as you start cooling these atoms down, slowly the wave nature becomes dominant. And if you keep going colder and colder, there comes a critical temperature where suddenly these matter waves starts overlapping, uh, and it makes a giant matter wave. So all atoms start to behave identically, and you can treat a collection of atoms as a big macroscopic object. In other words, if you had let's say, a box to contain your atoms, let's say you have a harmonic. So when you do your quantum mechanics course, the first thing you will learn is quantum harmonic oscillator. So there you will learn that you have discrete energy states of this harmonic oscillator. So when you have atoms at high temperature, all these states are occupied, and there is certain probability associated with occupation of each of these states. But when you start cooling down and when you go below this critical temperature, suddenly all the atoms are occupied in the ground state, and this is called as macroscopic occupation of the ground state. And this is the phenomena known as Bose-Einstein condensation. That it's the lowest energy possible, um, and that's the phenomena. So this is all good, but then why is it a big deal? So just to give you an idea, the term that decides the when this transition happens is called phase space density, and as I say here, it should be of the order of 1. So without going in details, if you take a gas at room temperature, the phase space density associated with that is going to be about 18 orders less than 1. So you can see how cold you have to go in order to uh, you even think of achieving Bose-Einstein condensation. So it's not so easy, and to understand why it's a big deal, we have to go a little bit into history of quantum mechanics or Bose-Einstein condensate. So just to summarize, the first time this idea was put forward of this phenomena of Bose-Einstein condensate was in 1925, and the first experimental demonstration came in 1995 in Colorado Boulder and MIT in the US. So it took 70 years to achieve first ever Bose-Einstein condensate in a laboratory. And since 1995, even though field and technology has grown so much, uh, it's 25 years later that we could make it from home, and also just recently NASA has made it in space. So even now, after 25 years after the first demonstration, it still remains a big challenge. And I will tell you why it still remains a big challenge. Be- So what happened? Because for that you need to know what happened in these 70 years. Why it took 70 years to build first Bose-Einstein condensate. So if you look at the history of quantum mechanics, in 1923 was the first time this matter wave concept was uh, put forward by de Broglie. Around the same similar time in India, Satyendranath Bose was doing some calculations, and he was looking into photons, and he rederived the black body spectrum for photons, and he submitted a paper which kept getting rejected because it was different from the very well known Maxwell Boltzmann distribution back then, and they didn't know why. But he sent a letter to Albert Einstein, and he realized that there is something interesting happening here. So what Einstein did was extended Satyendranath Bose's work on photons to massive particles like atoms or electrons. So, and then he realized that there's this peculiar feature that will happen when you look at Bose-Einstein statistics for certain temperature. This macroscopic population of ground state is going to happen, and this is the phenomena that they predicted. But it was a bit unimaginable at the time, and a lot of people didn't believe that this will actually exist in finite systems. So Einstein received a lot of criticism. People were saying, "Oh, this has only imaginary existence," and Einstein himself, to a certain extent, accepted this criticism. So there were between 1925 and about 20 years after that, people still didn't believe that this could exist. And the real quest for BC really started in 1960s when first time superfluid of helium was observed. So there is a connection between superfluid helium and Bose-Einstein condensate. Just a spoiler alert: Bose-Einstein condensate is also some sort of superfluid. So people started making these connections, and superfluidity was observed in experiment, and then people started believing that okay, even Bose-Einstein condensate can exist. And then there was a lot of theoretical work done, and they thought the easiest atom to be condensed could be hydrogen. But there were a lot of experimental troubles, because when you contain a hydrogen gas in a chamber, it collides with the walls itself, and so you cannot keep cooling down without uh, atoms hitting the walls of the chamber. And they couldn't. They were extremely unsuccessful. Not just getting condensate, but going even closer to getting condensate. So there were a lot of ideas about how we can do. So one idea they had is maybe we have to isolate the atoms from the chamber. So you have to make a trap with electromagnetic fields, which will contain the atoms in a specific position. So you can have a glass or your chamber, and you can tell atoms to be just at the center of the chamber. So you can use electromagnetic fields. Like the first proposal that came was magnetic trap. So using magnetic fields, you confine the atoms in one particular position. However, there were problems with this idea as well, because the atoms were at maybe room temperature or a little bit colder. It was not enough. They were just escaping this trap. You can imagine like having a bowl and very hot liquid in it, and if the liquid is shaking too much, it's going to spill out of the bowl, and it's not going to stay in the bowl. So this is exactly what was happening. And then they realized, okay, we need to cool the gas a lot before we can even imagine trapping it, and before we can think of condensing it. So the real game changer happened in late 70s or early 80s, when people started using laser beams to slow down the atoms. And this was a real game changer. So 1985 was the first time people after invention of laser cooling of atoms, that people thought, okay, maybe Bose-Einstein condensation is not very far. And this became such important discovery that I think I will spend one slide on this because it's extremely important. And to this day, the first step of any Bose-Einstein condensation experiment is magneto-optical trap, which is basically laser cooling of atoms. So this was demonstrated in 1985, but it received Nobel only in 1997 because they thought this technique didn't have application. But first Bose-Einstein condensate was demonstrated in 1995, and then the Nobel Committee thought, oh, okay, this technique is useful. So they gave a Nobel to scientists who discovered laser cooling of or demonstrated laser cooling of atoms. So what do you mean by laser cooling is basically your atoms are moving at certain temperature, they are moving randomly with certain velocities. So if you reduce this velocity spread or randomness of the velocities, you're essentially cooling the atoms. So and how you're doing is you're using lasers to reduce the velocity spread. That's why it's called laser cooling of atoms. And the concept of laser cooling is very elegant, and I'm going to just ignore the math part of it, but I'm just going to briefly explain this. That if you have an atom with two energy states and you shine a resonant laser beam, what it's going to do is absorb and re emit. So if you take an atom which is moving with velocity v in this direction, and if the laser photon comes in the opposite direction, what's going to happen is because of this incoming momentum of the photon, uh, the slight atom is going to get imparted the momentum of the incoming photon. So the velocity of atom can be reduced by the same amount. So when this process happens several times, maybe 10 to the 6 times, 10 to the 7 times, after so many events, the atom eventually gets slowed down. And just to see the power of this kind of radiative force, you can get the acceleration by such events, which is 4 orders more than gravitational force. So this is a huge force, and it's extremely powerful technique to slow down the atoms from room temperature to microkelvins in fraction of a second. And this has formed the basis of cold atom community, and it's the first step of any cold atom experiment to have laser cooling or magneto-optical. So this technique only cools the atoms, but if you add further fields, you can even trap them. And I'm not going to go into the details of that, but uh, this is when people realize, okay, now the Bose-Einstein condensation is not very far. Still, it took
So I
almost
have a
a
question.
decade. Yes.
Can't the laser also accelerate the atoms as well instead of just decreasing their speed? They can also increase their speed as well.
Yes, it can. So you need to have a clever scheme of um, laser beam arrangement. So this is a very simplistic picture of having just one beam. So what happens is if you have velocity of atom v, and eventually it will be slowed down by this laser, but once it's slowed down to zero, it's going to start accelerating in this direction. And you're absolutely right that it's going to accelerate it. But then you can have another beam on from this direction. So a counter propagating pair of laser beams can make the atom stationary in one dimension. And now if you have a pair in all 3 dimensions, you're going to have a 3D uh, slowing down of the atoms. So this way we can avoid laser accelerating the atoms. Does that, is it fine?
Yeah.
Okay. So 1985 was laser cooling, but it still took 10 years to finally get to Bose-Einstein condensation because the demonstration of laser cooling itself opened up a whole new field of quantum optics and light matter interactions. And there was amazing science done during those 10 years. And they developed the techniques of laser cooling further and went lower in temperatures. But that was still not enough. What made a huge difference was this technique called evaporative cooling. It's basically how you cool your coffee in the cup, that hot atoms escape from the cup, and rest of the remaining atoms rethermalize to lower temperature. So this was a very elegant cooling mechanism that was demonstrated by Ketterle in MIT, and this was a big milestone in getting. Once this technique was established, it was very easy for them to show Bose-Einstein condensation. So almost happened parallelly in two labs across US. So first one was rubidium atoms in Colorado Boulder, and just a few months later, sodium atoms also were condensed in MIT. So after these first demonstration of Bose-Einstein condensate, this field has grown rapidly. I mean, amazing experiments have been done with using these Bose-Einstein condensates. It sort of gave a new platform to explore all sorts of different physics. So I'll just give you an example. So you can think of it as, that how you think of optical laser and a difference between LED and a laser. It's same as a cloud of cold atoms and a Bose-Einstein condensate. So whatever you could do with photons, now you can do with Bose-Einstein condensation. So this is an experiment where Ketterle took two Bose-Einstein condensates and made them interfere, similar to what you do in optics. So it's very cool that you can do interference, diffraction, and all sorts of cool things with now atoms. It also served as a excellent system for studying condensed matter physics because there are no impurities, unlike the samples of condensed matter systems. You have ability to precisely manipulate single atoms also. Uh, so you can make like different lattice potentials or interesting systems and play with individual atoms, their parameters, and you can do different condensed matter experiments which were not possible before. And the recent uh, use or recent application of Bose-Einstein condensates are in quantum technology, and this is a very, very upcoming field right now. Say in last few years, especially in the UK, there's a whole community doing research on quantum technology where you want to use both BECs as a tool or as a sensor because they're such sensitive objects. That's the reason it took so many years to achieve them. But we can exploit this property of sensitivity to environmental fields and use them as ultra sensitive sensors. So one example is what we were trying to do in Sussex was we wanted to use these BCs to probe the local magnetic field. Now these magnetic fields are going to be extremely tiny, which are extremely difficult to be measured by existing sensors. So just to give an idea of how small the magnetic field would be, we are talking about femtotesla, picotesla. So several orders magnitude smaller than the Earth's magnetic field, for example. Earth's magnetic field is half a Gauss. So like at least 8 to 10 orders smaller than Earth's magnetic field. So what we wanted to do is have a surface and bring our BC very close to a surface, and we image this BC, and by changing the uh, by observing the changes in the BC, we can tell what is the magnetic field. So we call this magnetic field sensors. So the research that we were aiming in Sussex was based on this. Now this is very technological application, but what I'm doing in Weizmann is a bit more fundamental kind of research where we are studying how if I shine a laser beam onto all condensate, what happens, how the light interacts with the atoms, or how atoms interact, how atoms affect the light itself. So here I'm doing more fundamental kind of research. So the point I want to make here is Bose-Einstein condensate is just a tool, and there are several laboratories all over the world which use it for different reasons, either for technological reasons or for probing fundamental physics reasons. So it's a very rich platform that's become accessible to us now. So now this is just a last slide. I want to just show you some pictures from our lab in Sussex, and maybe give you an idea about complexity of these experiments. On paper, these ideas seem very nice and elegant, but in reality, it's very complicated even now to get VC. You can see on the left here, we have all sorts of lasers and mirrors and polarizing optics to prepare the laser light to exact frequency, polarization, and power, etc. So this is all for preparing the light for laser cooling. Once the light is prepared, we send it through optical fibers to the experiment site. And here you can see our experimental chamber and lots of wires going around. I'll tell you why. But this is a vacuum system, and as I said in the history part, that with hydrogen they couldn't succeed in getting condensate because it kept interacting with the walls. So we know that we need to go to ultra high vacuum level so that atoms that we want to condense don't have unnecessary collisions with background atoms. So we want a very clean environment. So that's why we have this ultra high vacuum system here. And then, of course, some more optics and a lot of electronics, because we also have magnetic fields. And magnetic fields are generated by passing current through different kinds of structures. So we have different types of magnetic field profiles which are necessary for different stages of cooling and trapping. So all these current carrying wires are situated around the chamber. Some are even inside the vacuum chamber, which creates a whole other set of problems. But you need a lot of electronics to control all these currents precisely. Timing is extremely important in these kind of experiments. And on this little screen here, you can see actually the atoms trapped in a magneto-optical trap. This bright blob in the center of the screen is atoms fluorescing, which are trapped and cooled in the center of our chamber. So when we want to remotely run this setup, you can imagine how many parameters that we need to control. It's extremely complex sequence, and there are different timing problems, different equipments that we have to keep a track of. But fortunately, we had this system in place where we could monitor all the parameters from home and even control our experiment from home, which made it possible to get BC from home. Okay, so I think that's all I wanted to talk. If you have any questions about anything, I'm happy to answer.
Vijay.
Yes, ma'am. There are a few questions, and the first question is from Arpita Saha. Arpita, do you want to unmute and ask the question?
Arpita is not.
Okay. So a question was, could BEC
Hello,
be...
ma'am.
Hi. Yes. Please ask Arpita.
Hello.
Yeah.
Okay. Hello, ma'am. Could BEC be used for quantum computers too?
Yes, there's a lot of quantum computation also going on, but I think the most common system that they use for quantum computing is trapped ions. There are, I don't want to go into details, but individual, so what they call qubits is made from single trapped ions. That's the most popular approach right now to quantum computers. But yes, it's a similar idea. Yes.
Okay, ma'am. Thank you, ma'am.
Next, Akshita, you can ask the question.
Yes, ma'am. So my question was, when we form the Bose-Einstein condensate, how do we achieve that low temperature? And like, are there more multiple options of doing that?
So that's the laser cooling. So first step is laser cooling. So we start with room temperature or even hotter atoms, and once you shine the lasers with shine different lasers on the atoms, um, you need to have like the right frequency, right polarization to achieve this. But once you do that, your temperature reduces from room temperature to maybe 6 or 7 orders lower. So microkelvin, for example. And then you have to use this other technique called evaporative cooling, which is typically done in absence of uh, laser fields. So you need several cooling stages, but most of them involve lights or magnetic fields or microwave fields. That's how you lower
Okay.
the temperature.
Thank you, ma'am.
Clinton,
Yes. Ma'am, how much did the whole setup cost? And if it was done at home, and if the setup is very dangerous, then what safety measures were taken to uh, prevent
Yeah,
any
so,
kind of fire or something?
so you can't take this setup home, unfortunately. It's okay. To answer the first question, it's very expensive. Um, each laser can cost between it's tens of thousands of pounds. Um, I cannot even give you an estimate. So the whole lab might be like $1 million or even more. So you can't transport. Obviously, you cannot. They're extremely sensitive experiments. You cannot run them without a laboratory controlled laboratory environment. Uh, so what we did was all these equipments are connected to a computer. So all you can do is you can operate the computer from home. So we don't take the experiment home, but we just take the control home and control it uh, from home. So that's what they do in NASA as well. That they have this setup. Their setup is a bit miniaturized because they knew they have to fit it in a box and send it to space station. So there's a lot of work going on miniaturizing these setups also, because in future when you want to make quantum sensors, you don't want a sensor to have this whole occupy this whole room. So there is a significant effort going on to miniaturize these systems, but right now they are occupying a whole room, and you can't easily make them smaller and reduce the volume of the system. Does that answer your question?
Yes, ma'am. Thank you.
next, Chintan, you have a question, right?
Yeah. So, ma'am, my question was this.
Mhm.
The basic thing, one of the most important, what is required, what I can make out from the talk you did was the temperature should be extremely low to form a Bose-Einstein condensate. So
Mhm.
if we are creating it on Earth, that it's going to be like we have to create it like manually. It won't occur naturally. But as we know, space can get really weird. We know there are some ridiculously high temperatures that can be found in space, but there can be also very low temperatures that can be found in space. So do you think at such if there is a right temperature in space, would Bose-Einstein condensate form there naturally?
So other than temperature, it's also density that matters. And as far as I know, space is about 1 or 2 Kelvin, and here we are talking about nanokelvins, which is 9 orders smaller
Yeah.
than space. So it would be extremely unlikely to have it naturally happening. And the other requirement is isolation from its environment. So you need to have your atoms isolated from any kind of environmental effects. So that's why we need these traps. So traps are basically magnetic fields or optical fields. So you must have heard about optical tweezers, how laser light is used to hold or trap particles. It's the similar concept. You can use magnetic fields to make such traps. So what they do is they hold the atoms and prevent them from interacting with walls of your chamber or any other atoms in the background. So it's all. I have to say it's not possible to have it occur naturally.
Yeah, man, even I thought, but I thought like I wouldn't know anything. Why just not I ask? Like I know it would be a stupid question, but I just thought if
No,
it
it's
can
fine.
form.
It's fine. No problem.
Yeah, next question, Satish, you can ask.
Hello. Hello, ma'am.
Yes.
My question is that what is the physical relation between Bose-Einstein condition and statistical mechanics? And could I explain it from statistical mechanics?
Sorry, can you repeat the first part? What is what? Hello, can you repeat the first part of your question?
Amruta, it is there in the chat box if you can see the chat box.
Okay.
Satish Kumar Gautam has put that question there.
What's the idea?
Ma'am, can you hear me? Ma'am, hello?
Yeah,
Yes,
now I
Satish
can hear you.
Kumar.
Yeah. What is physical relation between Bose-Einstein condensation and statistical mechanics? And could I explain it from statistical mechanics?
Yes, the first work done by Bose was from statistical mechanics point of view. That's when they came up with Bose-Einstein statistics. So you have Fermi-Dirac statistics. You have Bose. So Bose-Einstein statistics works for bosons. So this is for particular kind of particles, but you have different Maxwell-Boltzmann statistics or Fermi-Dirac statistics. So yes, the first idea came from statistical mechanics.
Okay, ma'am. Okay.
Next, Sarah, you can ask the question.
Hello, ma'am.
Yes.
So my question is, what was the element or material you used for creating BEC? Also, why that specific material only?
So typically, alkali atoms are the most famous in our community. We use rubidium atoms, but as I said, the first condensation was demonstrated using sodium atoms and rubidium atoms. So alkali atoms, why? Because they are bigger atoms, but they have just one valence electron. So you can treat it as hydrogen atom. So why is it better? Because first of all, because the electronic structure resembles hydrogen atom, the spectroscopy is like the spectroscopic structure is very clean, and it's easy to use these atoms compared to atoms with complicated energy levels. So that's why in our community alkali atoms are preferred. Specifically, why rubidium is purely a technical reason, because the lasers, what we call external cavity diode lasers, are available very easily now for rubidium wavelength. So that's why it's easiest to do rubidium atom. But people have done condensation of potassium, sodium, lithium, even hydrogen now. So many atoms have been condensed so far in last 20 years. But rubidium remains still the most popular choice.
Okay, ma'am. Thank you.
Durgesh, you can ask the question.
Hello, ma'am.
Yeah.
Can we form BEC using fermions?
Yes, there are. It's not called BC, but there is a fermionic degenerate gas, and there are different kinds of techniques involved. And I'm not expert in that at all, but it's a whole different subfield of fermionic studies.
Okay, thank you, ma'am.
So some people, like for as I mentioned, which atoms you choose depends on what experiments you're interested in doing. So some people want to study bosonic fermionic interactions. So you can choose element like potassium, which has different isotopes. Some of them are bosonic, some of them are fermionic. So when you have atomic source inside your vacuum chamber, you have access to both isotopes. So if you're interested in doing that, then you can choose potassium, for example.
Hello, ma'am. Sorry for disturbance. Fermions do not obey Pauli exclusion principle. Why you are recommended fermions?
Sorry, what's the question?
My question नहीं है. Fermions do not obey Pauli exclusion principle. Why you are recommended fermions?
That's why I said that fermions do obey Pauli exclusion principle. That's why it's not called Bose-Einstein condensation. It's a different statistics called Fermi-Dirac statistics, because they cannot be trapped into single quantum state, because Pauli exclusion prevents it from having them in same quantum state. But you can reach very cold temperatures by some other techniques using fermions. So it's not called Bose-Einstein condensation, but you can get to very, very low temperatures in fermionic systems as well.
Next, Yash has a question.
Is there any relation between BEC and conductance at a very low temperature?
No.
BEC and what?
Conductance.
I have to say this, I'm not aware of this field. No. I mean, there are a lot of fancy effects being studied in using BCs, but yeah, it's a vast field, and I'm not aware of these experiments.
Next,
so there are a lot of experiments probing superfluidity properties of BCs. It's a kind of superfluid, and people have studied vortices and things like that in BCs. Yeah.
Next, Professor Pathak, you may please ask the question.
I can read on the screen. How to screen off the geomagnetic field.
Yeah, I'm Professor Pathak from Haridwar. I would like to, of course, I am not in this field, but the geomagnetic field is very strong, as you told, it is half a Gauss, and you inside your apparatus, you need only pico Tesla. So that will be interfering, but how do you screen off this geomagnetic field? Because you are doing in the lab, so geomagnetic field must be there.
Yes, so either we compensate the fields, so we have a lot of compensation coils in all directions to nullify, and we have some techniques to make sure that we have zero magnetic field inside our chamber. But if not, we can always do, so the actual trapping fields that we use are much higher higher value fields. So for magnetic field sensing, the trapping potential is way larger than the residual geomagnetic fields. So you can always do a reference.
I think you mean that you apply the reverse magnetic field of that geomagnetic field, reverse of that same order. I think that you mean.
Sorry, I didn't fully understand that.
Look, what I could understand that you apply the reverse magnetic field of the geomagnetic field. So to compensate, to nullify it. You mean that?
Yes, yes. That's one way. The other way is to do comparative study, where if you want to measure a field from a sample, because you can just compare it without the sample, where the sample is absent, and because geomagnetic field would be a constant, by doing comparative study, it would get cancelled off, and you can study the effect of the current.
Thank you.
Neil, you can ask the question.
So I just have two questions. One, is there any possibility of perhaps cooling down radioactive isotopes? Firstly, as a probe of because you can do atom interference, could that be used as a probe for the strong force or the weak force? And also, could the decay rates help in measuring, say, the fine structure constant more accurately? That's the first
Yes,
question. The
this
second
is
question
the
was.
whole field of precision studies that you described in your question. So there's a lot of research happening on different isotopes and measuring fine structure constant accurately using ultra cold atoms and doing interferometric studies. You can there are so we were looking into magnetic field sensing, but there are groups doing gravitational sensing, gravimeters as they call, where you measure G very precisely. So this is the whole field of quantum metrology, as they say, where the idea is to measure constants very precisely.
Also, what was the rationale behind NASA creating BECs in space?
Yeah, so that's a very good question. So the way we probe these condensates or cold atoms is, we make them in a trap which is formed by electromagnetic fields. But to image them, what we do is we switch off all the traps and let them expand under gravity. So we have a camera looking at, let's say we have a camera and our atoms are trapped at the center of a chamber, and we release them and let them fall and expand. And by studying this expansion, we can deduct many properties of the condensate. So, but this camera is going to have a limited field of view, and because of gravity, they are going to go out of field of view within short time. So in space, what they want to do is, because there's no gravity, you have longer interrogation times. So you can do some experiments which are not possible on Earth. So that was their motivation to do some studies using cold atoms, but in absence of gravity.
Thank you.
Panay, you can ask the question.
Hello, ma'am. So my question is, what was the idea behind declaring BEC as a completely new state of matter? Like, to be more precise, on what parameters it was declared fifth state of matter?
It's kind of like you have plasma. It's kind of an exotic state of matter because it has the properties of condensate are completely different than existing states of matter. So that's why it had to be named as a new state of matter. And the quantity that defines is the temperature. So below this critical temperature, it cannot be defined by our regular rules of classical mechanics. You need to start looking into quantum theory to be able to describe this phenomena. So the energy scales is the criteria that defines condensation.
Thank you, ma'am.
Sribo, you may ask the question.
Hello. What happened to a light in an extremely low temperature?
Okay, so light is basically photons, and photons are bosons as well. So there was an experiment in our field a few years ago where they sort of showed Bose-Einstein condensation of photons. But it's a bit tricky because photon number is not conserved, so it's a bit different kind of phenomena, and it's a lot tricky to have VC of photons. But essentially, you can treat photons as bosons and treat them in the same way.
Okay, thank you, ma'am.
Ma'am, in the PPT, you had mentioned that we use a harmonic potential, right? And also, like while doing simulations and all, we use a harmonic potential. Like, why exactly are we using that particular potential? Or
So in reality, we just approximate it to harmonic potentials because we know how to solve quantum mechanical harmonic oscillator. So it's just easier system to deal with, and the way we make our traps are they within some approximation they can be treated as harmonic potentials. We do so the way we do is we simulate these potentials. So if I have certain current in some geometry, how would my magnetic field profile look like, and how atoms can be trapped? And we do these numerical simulations before doing it in experiment. And yeah, the shape resembles harmonic oscillator.
thank you, ma'am. Does anyone have any other questions for ma'am?
Ma'am, I have a doubt.
Mm-hmm.
Can we create any unusual compound or any alloys using ultra cold chemistry using BEC?
You can create molecules, like cold molecules. So there are some experiments where, in our experiment, we were using only rubidium, but if you have two atom sources inside your chamber, like potassium and rubidium, you can sort of create potassium rubidium molecules, but you can't create any arbitrary compound. I mean, you have to take into account compatibility with laser cooling and available laser sources, etc. Because the only accessible material that you have is what you put in your vacuum system. You can't arbitrarily make a compound. No.
Okay, ma'am. Thank you.
Ma'am, there was a question in our YouTube chat, and that is, how can we have wavelengths for atoms trapped for BEC if velocity is almost zero? As per de Broglie wavelength, it is inversely proportional to velocity.
How can we have wavelength?
Yeah, the question was, how can we have wavelengths for atoms trapped for BEC if velocity is almost zero? And like follow-up was, as per de Broglie, wavelength is inversely proportional to velocity.
Yes, so if you have very, very low velocities, you're going to have very large de Broglie wavelengths. Large meaning at the scale of atomic sizes, where the wave packets from each atom start to overlap. And that's because of the narrow velocity spread.
That's all.
Any more questions? Yeah, ma'am. So like final question from the society. It's a bit general question. Like, what advice would you give to the young scientists who are present here? In terms of choosing a field to work in, or like in terms of the field they're currently working in?
The advice is what I said earlier, that get exposure to many, many fields before narrowing down your field of research. You can, of course, there are cases where you do PhD in one field and in your postdoctoral research, you completely shift your field. It's not impossible, but then that adds to your timeline if you, it it's going to be slower progress than if you don't shift the field. So I would suggest that consider all the criteria where you want to do PhD. Other than, of course, the topic that you're passionate about is very important. But for example, if you want to do PhD abroad and then eventually you want to come back to India, then you have to take into account whether there is any scope in India when you come back, or if you want to keep an option open to move to industry, for example, then you have to think about if the field has so many industry options available. What are if you what are the options available if you decide to move out of academia? So I would suggest, yeah, think about all these things other than what you're passionate about and make a optimized decision.
Thank you so much, ma'am. I guess we'll conclude now.
Um, Thank you so much, ma'am. We have Jyoti ma'am who has joined us, our HOD. Jyoti ma'am, would you like to say a few words?
Hi, Jyoti ma'am.
Yeah, hi Amruta. Sorry, I couldn't be here at the start of the talk because I was busy with some, administrative kind of compulsions, attending
Okay.
academic council meeting, which I couldn't avoid. So yeah, I'm extremely happy to have you here and talk to our students. And this advice that you gave in the end about how they should narrow down on their PhD topics and all is extremely valuable. And coming from younger people, it kind of really brings down the ground realities of today's times. Because when we did our work, maybe our considerations were somewhat different. But
Yeah, I think
yeah, so I'm really sorry that I have missed your whole talk, but I'm sure recording is there, so I will look at it later on. But thank you very much for coming, and we are really proud of you.
thank you
And
for inviting me. It was a pleasure to talk to students.
yes, of course, it is our pleasure to have you here, and I'm sure the talk must have gone splendidly. But I excused myself from there so that I can at least talk to you for the last 2 minutes. Yeah. So very nice to have you here. Yeah, Bijin, you all can proceed with your proceedings however you have decided to go about it.
Thank you, ma'am. We'll have Janelle to propose the vote of thanks.
Sorry?
So thank you so much, ma'am, for joining us with this inspiring session. We were honored to have you here to talk to us, to tell us about your journey, right from St. Xavier's to Bose-Einstein condensate, right in your living room. You did honors here, you gave various entrance tests, and also you worked with some foreign reputed institutes, which we find very much motivating for us. We know when we meet any Xavierite, we feel honored because that's the aura of our college. You made a breakthrough right from your living room and proved that researches can be done in inaccessible environment, right in space. And NASA even did it. Whoa. Not everyone was aware what Bose-Einstein condensate is actually, but you explained that it's just a cloud of millions of atoms at sub-Kelvin temperatures, which are acting like a common quantum entity, which was pretty much lucid and tranquil. You gave us a timeline about the history of Bose-Einstein condensate, right? It took 70 years for discovery, and that's something we get to find determination from. That microscopic science is right interesting. You have opened the doors of curiosity in the minds of students, and you are even motivating them. And we can see that right in the chat box from the questions of the student. Thank you, ma'am, for doing this. I'm sure we will imbibe this indispensable experience, and your advices would surely enhance our future. I would also thank our department teachers, the Department of Physics of St. Xavier's College, and also the Society of Physics for providing us with this awesome session. Also, thank you all the audience for making it a great success. Thank you.
Thank you very much.
Thank you so much, Janelle. Thank you so much, Amruta ma'am, from the department and the Society of Physics as well. And unlike normal sessions, now for our conclusion, we'll only ask people to start leaving the room. So,
Okay, thanks again. It was very nice.
thank you so
Thank you,
much, ma'am.
Amruta, for accepting our invitation and coming here and giving a very good picture of what is research work to our students. Thanks a lot.
Yes, I'm very honored. And if there's any questions anytime, let me know. I'm ready to help about
Yeah, yeah.
applications or anything. If you need any information, I'm
Um,
always available.
Sure. Yeah,
uh,
sure.
excuse me, ma'am, Amruta ma'am, could we share your email ID with the master's students in case they have any uh, doubts or
Yeah,
any
email
guidance?
ID is fine. Yeah. Yeah.
Email ID? Okay, thank you so
Yes.
much, ma'am.
Okay, all the best, everyone.
Thank you,
Thank
ma'am.
you.
All the best to you also.
Ma'am, I
Thank
suggest
you.
you look into the chat box to all the students are showing their gratitude.
Yes, I can see a lot of.
Yeah.
Okay, I'm gonna leave the meeting now.
Okay, thank you, ma'am. Thank you so much, ma'am.
Thank you so much, ma'am.
Yeah. Bye.
Bye.
Sure. Yeah.